Yo, 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 yo. What's up, guys? I'm Abhishek. I'm back again to yap about my AI projects to my lovely friends who are watching this video. Anyway, a quick update about what's been happening in my life, even though you didn't ask for it, is that I started my internship at AXA in France. Really, I'm not going to talk much about it right now because I'm going to keep all the climax for later, bro. By the way, AXA. All right. And then another thing I want to talk about is the weather, bro. Bro, the first day I landed in Paris, it was so hot. It was so goddamn hot. It was like 37 degrees, and I did not have a fan at my place. And guess what? None of Paris does actually. They do not have air conditioners. They do not have fans. And I try to get one from the supermarket or like the market, and guess what? It's the stock is over. I'm like, bro, what do I do? I had to wait like 4 days and then I get it. I don't get what's the deal with Europe and air conditioners and fans, but damn, bro, you gotta like be prepared next time. I don't know that's gonna work out, but okay. Another thing is that I'm currently working on deciding a topic for my master thesis. I'm gonna work on mainly, I was thinking of working on mainly two topics. One is the emotion detection in real-time videos, or on or basically what is it? Yeah, basically document extraction. I gotta find particular use case because both these fields are very very saturated, I think, right? And I gotta find something that I can do really that's kind of impactful, and I get to learn some cool stuff. Anyway, I'm gonna stop yapping about myself, but I'm gonna continue yapping about my AI project. So let's go and jump onto that, right? Oh no, no, it's here. All right. So, brief intro. This project was done with my school, and the project company called Datacraft and Edges. We worked to do wetland segmentation. Uh, I'm gonna try to keep this video at like 30 minutes max. I'm gonna go through it at a very high level, and I'm going to talk about the coding at high level as well, but I'm gonna show you some few scripts that I really think it's cool. And I want to give a big shout out to my team, Dilara, Erwin, Henry, and Steven. A lot of research went into this, and basically a lot of discussions and lot of presentation materials and lot of stuff that we had to like present. So they took care of that, and I was working on the coding part, and I really enjoyed them. And so big shout out to them. Uh, Anyway, let's go into the matter, right? Like, why do we give a shit about wetlands? Well, for a fact, why do I care about wetlands? It's because wetlands are home to capybaras, bro. And capybaras need to be protected from us because they are the economy of the internet, right? And that's how the memes these days are coming in because of the capybaras. So please save the capybaras. Yeah, bro. Jokes aside, basically, wetlands have like around like 5 to 10% of like the Earth's land, and these 5 to 10 has around 30% of the carbon, right? So this is what all the biodiversity mainly thrives on. So you need to keep it protected, bro, and save the capybaras, bro. You get it now? Okay, the challenges and project objectives and goals. Basically, we had to do wetland segmentation using satellite imagery, which was basically Sentinel-2. Some common tasks they told us to do was use some deep learning architecture for this. Since this was like a pilot project, we did not want to, uh, since it was a pilot project, we did not have like a accuracy that we wanted to achieve. It just like the data pipelines and the methodology and the automation part that and the research, like how do we come up with the solution that we were part of. So I'm just gonna talk about that in general and what is the impact that we wanted to deliver. Basically, next by next year, or in the next 5 years, if you see the population of capybaras increase by 100%, you can come and thank me, bro. Uh oh, web app. You guys want web app, huh? All right, let's go to the web app. So go to the Hugging Face page on the link mentioned below, and you will end up here. What do? You can upload an image or you can upload a TIFF file. What is a TIFF file? TIFF file is basically a satellite image file, or it can be like a one format of it, right? And basically, I'm gonna show you an example. I uploaded it, and let me click the analyze image. Wow, look at this. This is the image, right, of the ground, and I also see a cloud. Uh, And then this is the ground truth. Basically, the yellow part is the wetlands and purple part is the non-wetland area. And this is the predicted wetlands. This is what my model does. And as you can see, it's kind of bad. I will talk more about the details on why it is bad, but mainly it is because of class imbalance and the data quality. Okay. Um, some statistics about it, right? Uh, In this image, it tells me that there's only 10.35% of wetlands and it also detects a cloud. So I wanted to tell specifically that we made two models. One was for the cloud and one was for the image segmentation of wetlands. So you can see double that. Um, and some evaluation metrics to look at, which is wetlands IOU, which is like 12. Terrible, terrible. Again, I'm not gonna blame everything on data, and imbalance, but I honestly can't tell you anything else because that's what they gave us, and they also from their end told that yes, this is it, and I can tell you the reasons next, but for now. So, but basically the IOU, wetlands IOU, it's this is for the wetlands. Then there's a background IOU, and then there's an average IOU, which is the average of the background and the wetlands together. So, ideally, we would like to increase the wetlands IOU by maybe like 50, 70, 80. That would be like a good score. But since this was the pilot, they were okay with the whole implementation of it. So that's the web app in a few words. And yeah, let's go back to the presentation. Uh, Data overview. Let's come to this. So I had like we got like 36 satellite TIFF files, okay, and we got one shape file. So basically, this 36 image TIFF files were basically of the same land from January 2021 to December 2023, right? And these were the masks. So basically, this falls on top of this, right? So one shape file and 36 Sentinel-2 images that we got, and it has like 10 bands of it. The dimensions were 62 height and 357 width. Very bad resolution. Okay, very bad, terrible. 10 bands that we got. Ground truth was the one shape file. Class imbalance, another big challenge that we had. Out of this whole image, you see that only 9% is wetlands and the rest is non-wetlands, right? And Yep, that's about the data. Now, coming to the data processing pipeline, which I think is the most crucial part of it and the most annoying part of it, and also the most rewarding part of it. So, definitely look into this with a lot of importance and stuff because I think this is the main part of it, right? So we did it in three ways. One is the patching, the train test validation, and we also discovered something about clouds. So starting with the patching strategy. So this image that you see, we divided into five different patches, right? Uh, why did we do this? We did this because we needed a lot of training data first to train the deep learning models, and second, we wanted to avoid data leakage. Since this is the same area's image file and it the only change is in the time frame of it, we got to make sure that there is no data leakage. So you can't, you know, pick like the last 10 images as like, the test set because it's the same area of land, right? So what did we do? We made five patches, okay, for the input image and the mask itself. So the input image would be divided into five patches, and then we would also get five patches of the masked image, masked or the target, right? And then what we do is the first three go into the train set. The fourth patch goes into the validation. The final patch goes into the test set. This was done to all the 36 files. So 3 into 36, uh, some 12 something, and then 36 into, I mean, one that is 36 validation and 36 test also, right? Uh, Yep. So, and then that's how we made sure that there was no data leakage, by the way. And then we had the cloud detection. This is like a future improvement scope, but we realized that since we have such a low score for our models, we also we figured out what was another issue that could it one of the reasons that could contribute to it was clouds, right? So cloudy images, clouds were there in a lot of images, like around 20% of the images had clouds in them. So we had to make sure that we remove this, right? So we made a cloud model and we made a image segmentation model. So basically in the future, when we have a data set, we have the cloud model that would remove all the cloudy images. And then out of all the images that we have, we would keep the training set, validation set, and the test set and make sure that there's no data leakage at all. Okay. Then some common feature engineering that we did is that we did some image preparation because most of the pre-trained models that we have seen take image sizes in the multiples of 32, right? So it is recommended, right? It keeps in 32. Like image size can vary, but it's recommended that to preserve it at 32. And the other problem that another thing that we did was padding. Since we divided it into patches and it was like, this whole thing was like 62 by 357. 62 was the height, so it's like 62 into 62, right? So we made it into 128. We resized the image, uh, and we padded the image. We did not resize. We padded it because sometimes if you resize these masked images to a higher dimension, like from 62 by 62 into like some 32, well, like 128 or 256 by 256, because of the bilinear expansion, the mass gets sometimes messed up, right? And because of that, it's not recommended to use resizing for these kind of tasks from lower to higher. So that is why I used padding over here. Okay. One crazy important point over here is the padding. And the other one was the band selection. For the pre-trained model, we can only use three bands, the red, green, and the blue. So only three bands. And for the cloudy images model, we used all the 10 bands, and we used it in a way that we needed, like, for one image, we needed like one particular value for each band, right? So how do you get like one particular value for each? band, because it's a lot of pixels, right? So that for that we get like coefficient of variation, so that you kind of understand how each pixel is different from each other, like the variation in it. Uh, uh, yeah, it's not. I can go more about, but I don't think I explained it right. Uh, but I wanted to. I will let you know it later, maybe. But do feel free to let me know, right? I will definitely come out and ask. And then we also made a small unit model with 12 different layers, right? Bands, one which is with the NDVI and NDWI, which is the vegetation index and the wetness index or something like that. Uh, so uh, these were the most common. Okay, there was one more. My bad. There's also data augmentation using the albumentations library. We did some rotations, some random cropping, and using the albumentations library, we ensured that the image as well as the masks are, coordinated together, and both of them are the changes are happening on both of them. You don't want the image to have one different transformation and the masks to have another transformation, right? So that was something that we had to keep in mind. So I think this was the most difficult part. I have kind of said it very easily in 2 slides, but trust me, that was a lot of work deciding how to fix this. And since we had like 3 months, it was not so easy to figure it all out. But yeah, that was it. I'm going to show you all the code snippets in the end. Uh, but for now, I'm just going to go you quickly through the slides and stuff. Uh, so this is about the models, the small unit that we made. It had 12 bands. Uh, and then for the pre-trained, we used the DeepLab V3 Plus with the ResNet 34 backbone, or the pre-trained weight, and UNet with the ResNet 34 backbone, pre-trained weights again, and the input were only 3 channels. For the cloudy model, we had like coefficient of variation and the model that we use to test and compare with each other, LightGBM, XGBoost, CatBoost, and so on. So, and the key metrics that we got to look at is the dice loss for the IOU and the image segmentation part. Uh, and for the metric, we use IOU. And for the cloudy model, we use the F1 score, right? And coming to the cloudy image model, we can see that we have LightGBM that wins it by an F1 score of 77. And if you see the Shapley values, we see that at an overall level, band 1, which is this is the overall level plot. We see band 1, band 2, and band 6 contributing to the cloudy model. And uh, at a image level, we see that band 2, band 3, and band 6 are contributing more to the cloudy image model, right? So that's about the cloudy model. And coming to the main part, the results of the wetland segmentation, we can see that DeepLab V3 Plus, which was FT means fine tuned, and TL means transfer learning. So the difference between transfer learning and fine tuned is that in transfer learning, we're just changing the last head, right? Like the classification head. That's it. But in the fine tuned model, we are just taking a couple of layers before that, like a couple, like 2 or 3 layers before it, and uh, also changing that, right? Like training it on those. So we have some more parameters, and we can see that there is a huge overfitting. Okay, like train IOU is average of these two, and it's like 70. Okay, but when you come to the validation, it's only 52, and test is 52 again. So between the train and the test, there's like a huge overfitting gap. And you can see that it's drastically reduced, like 42 and 8. It's like kind of really bad. And another model that I would like to give a shout out to is a small unit that we built from scratch, and it takes all the 12 layers, right? Uh, the train is 52 and the test is 46. Okay. So I think this one performed better in a way because it gives you the true actual values of it. Um, so the data limitations again, uh, the patches were really small, the data was really bad. We had constraints because of the GPU. I worked basically on Kaggle and with the P100 GPU, and that's all I had, um, and so on. And future directions, basically, maybe we should have tried ML models. I think maybe that would help, and try incorporating all the 12 bands for the other architectures like unit, and the normal unit pre-trained, and the deep labs v3 pre-trained. So I think those would be the things that, and getting a better higher resolution. Basically, I think this was the whole project in brief. Let me quickly go and show you through the code, right? So this is the final code that we had, and this is the basically the data preparation code, right? And let me show you the outline of it. It has the wetland segmentation, loading the satellite data, loading the, let's go to the loading satellite image. These are all the bands that you see. Okay, don't be surprised, don't be. And how did I get these two? It's because when I stack the first, second, and third, I get this. And this is to increase the contrast, because when you get typically in some image files, you need to do some cleaning because the pixel values mostly range from 1 to 256 mainly, and sometimes they go above and beyond that, so you got to make sure it's in that range, right? And when you do all that cleaning, you get like a better, clearer image over here, like you see here. Let's go to the shape file, right? You see the shape file, and you can see a lot of metadata as well, like, what is the geometry of the polygon, like these are the coordinates, okay? And what is the version, the shape, and I think most of this is not that useful for us, except one thing, which is the reprojection thing, which I'll talk about soon. Anyway, okay, I don't think check overlap. Okay, yeah, this is what I want to talk about. So since we have a separate polygon file and a satellite file, we got to make sure that the CRS is the same, right? Now you see that the CRS here is 2154 and the polygon is, they are in different. So you got to make sure that you reproject it in the same dimensions, right? So that you can overlap it properly, right? So you got to make sure that is all right and it properly looks correct. I used the help of ChatGPT because this was a huge bug that I wanted to fix, and so on. A little small widget that I built was this, and let me show you. So I like, let's see a little bit computer vision and stuff. Uh, let's remove the wetland mask. Let's put the band first. See, okay. So this is how it looks, like the red band, okay? Then I put the green band on top of it, and then I put the blue band on top of it, and that's how I get the image, okay? And then I put the wetland mask, and I see that these are all the wetland areas. These are all the red is the non-wetland areas. Okay, so coming to the visual satellite patches testing. I'm trying to make patches right now. Like you see, this was the input image in 5 patches, and then this is the same masked version of it, right? So basically, if you think about it, the masks do not change, right? The mask is always the same because the polygons are always the same. Only the land was always changing, basically. Okay. Uh, and then the first three, and this three goes into the train input and target, validation input, validation target, test input, test target. Okay. And then that was what I did for that. And then let's go ahead and see the cloudy train test validation. So again, the same thing I did, whatever patches we had, the train set, validation set, this thing. And what do? We make the coefficient of variation variable. We do some statistical tests to see which of the bands actually contribute to it mainly. Uh, a significant band 1, 2, 3, 5, 6, 9. Okay, for this thing. So it should be in that, right? And I make this model and I see the light GBM, the CAD boost, and the training, and I see that light GBM worked out the best. And at an overall, I see that 1, 2, and 6 are actually contributing most for the cloudy image models. So that was basically about the cloudy images. And coming to the deep learning model. So I had made all the, I used Kaggle. I had like, my train input, train output, validation input, validation output, test input, test output, and so on. Uh, do some albumentations, check if the all the uh, processing is happening in the right way. And then I'm doing the model unit pre-training, and you can see it, the loading, the whole thing. You can see the confusion matrix, you can see the predictions that it made, and then this is for the unit transfer learning part. Again, I just change that and I make the test curves. You can see the overfitting over here. uh, you can see this is like very very terrible results. uh, Coming to deep learning v3, again you can see the loss curves, it's like really bad. But you see that they do not bad over here. Transfer learning. So yeah, transfer learning does pretty bad, whereas the fine tuning does much better, right? And the simple unit part, let me come to that. Wait, small unit from scratch. Let's just see the results and code for this. Yes, I know I'm not being very efficient using notebooks and everything, but I had 3 months and I was mainly the main guy coding all of this, so I just made it kept it very simple. Yep. So if you guys have any doubts in anything after going through all the codes, please do comment below and reach out to me on my email or my LinkedIn. Right. And if you have like if you want to know something else about Paris or like any data science related stuff or the weather about Paris, do let me know still on the comments or like LinkedIn or YouTube. So yeah, that's about it. And I hope this video is 30 minutes long and I didn't. I hope I gave you some value or some insight and didn't bore you so much. Thank you guys again. See you, and I hope you liked it. Please do like, share, and comment if you guys want more videos or so on. Thank you.